Hello, folks. Um, this is going to be a bit of a chill stream. Hopefully, let me see if I can just get the level right here. Yeah. Can I get this like a near field here? Uh, Sorry, folks. Perhaps I should get a microphone stand or something. This isn't really an ideal setup right now. The working area is here on my left hand, and the display and the camera setup is yes on the side. So I need to rethink this sometime. Anyway, hello, folks. This is a random stream from me, Pavel, from Arcane Devices, and basically, what I've been thinking about recently is how hard would it be to make. Actually, that's the idea I was considering for a while, but never really had time to get into this. Basically, can we make a reasonable power supply with USB power delivery support for for a right or for your case perhaps? So there are things like that already on the market. Let me just grab a new Chrome here, and we can take a look at what the internet has to offer for us. Whatever. So let's look for USB PD rack power supplies. So let me just grab a little projector thingy. Window there. Yep. Like that, and I want this to be on top, like this. Right. Something like that. I've seen a nice one. I think maybe it was that's some eBay offer, but there was a nice one somewhere. I see there's a bunch of those. Yeah, see, like almost developers, they always use USB-C just for the device side port, and the USB-A for the host port. And I mean, of course you can do that, but it would be nice if like more people like actually implemented the dual role USB. I mean, I don't know how hard it is in practice, but it's there for a reason, right? Was it this one? No, that's something else. That's a bit of a late night stream for me. It's just kind of just because I'm procrastinating something more important. But I just wanted to talk to you folks, I guess, if anyone is actually watching this, which actually let me see. Wrong account. Okay, yeah. Yeah, I can find the let's try just USB C rack power supply. How about that? No, it's none of those. Oh, come on, Google. Really? That's it? Oh, that's tab. What? Rockets. Oh, maybe it was this one. No. Maybe. Like, see, this is just 300 milliamps. I mean, you can get a lot more from USB PD. I think. Actually, yeah, like 240 watts. Like, come on. Anyway. Oh, maybe that was the one. Also no. Constant, I think they have some nice stuff, but that's not it either. Let's see, all power modules. Is this sorted by time added? Perhaps. That looks kind of random. Yeah, sorry for the noise. I had to have quite a lot of gain, but otherwise, let's see if I can get this mic any closer. No, I'm afraid this will have to do. Okay. And this is a nice module too. Like, this is just the whole, MIDI to USB thing with a built-in power supply. I wanted to get this one when I was building my first modular, actually. Kind of ended up getting an FH2 just because it could do a little bit more, but honestly this is quite close. Yeah, so you get a USB device input here, and can this run from the USB power? I'm not sure. It has a DC jack here, so maybe not. Yeah, so something like this is I think pretty close to like the perfect. With what I would want in like in a combined module like that. If it could be powered from USB, that would be probably perfect. Polyend had a power module. Yeah, so this is actually also USB powered. 1 HP module. Okay, looks a bit awkward, but I guess that can work. What's this? What's this panel? Looks a bit strange. Yes, so I don't know. Perhaps we won't find it today. That's not really so important, but just wanted to give kudos to whoever made that one. Oh, that's a kit for a USB power supply, but let's see the headers here, but what's the actual supply? Oh, they have a GitHub. Okay, that's cool. Let's see. Better DC converter and remove 3 volts features. Okay, and what's that? So I know of tell me it will, but I haven't heard about this stupid USB ringing. Stupid USB power. Oh man, and Google is so useless nowadays. It's not even funny. What kind of cat this is for? Is this SkyCat? No, probably not, right? Yeah, it's Eagle. Let's keep looking. It would be nice to find out what that schematic was, but we checked out this one already. There is it. Now I found it. Okay, what's that? Oh, I guess it's just some kind of boost converter with the 5 volt input. Oh, it plugs directly to a USB socket. Okay, that's alright, I guess. So what I want to try today is just do something from completely from scratch, not using any store-bought DC modules or anything like that. And just to try it, really not as any kind of serious product design or whatever. Although if it works, we could consider that. Okay, so maybe let's just show you what I was thinking of. So the idea is basically just a boost converter, but we are gonna use a microcontroller for the just ignore the random stuff on the top. That's just some random stuff, but yeah, that's just 2 boost converters basically. So you get an inductor, right, a switch node, and then a capacitor to smooth it out, right, and then you can put a linear regulator afterwards to make the level more stable, but that's kind of optional. And then of course I would put what's it called, a crowbar circuit, just to protect from over voltage in case I screw anything up, since I'll be coding this myself. Uh, but why do it like that at all, right? So the thing is, since I am using the microcontroller, I could try doing another thing using the same chip, and that's basically trigger the USB power delivery or the power delivery protocol to tell the the USB power supply to give us more voltage. And like, so in the protocol, I think you can use 12 volts, 15 volts, and some higher levels, which some of them are optional. But anyway, if we manage to switch the external power supply to like 15 volts or 12 volts, depending on if we use the extra regulator here or not, we could perhaps like have this be a little bit more efficient in the sense that we basically can disable the switching circuit here and just rely on what the external power supply gives us. We will still need to make the negative rail, but that's that's at least one less thing to worry about. Yeah. And we don't really need a lot here. And like for the USB PD, I saw an example somewhere. I don't know if I can find this now. But there was an Arduino sketch or something to do it, or perhaps a library even. Power, USB power delivery library. Let's see. USB power delivery. There we go. So that just supports several STM32 boards. But it does work with ABRs too. Yeah, anyway, I think it just needs a UART anyway, so let's see if we have any kind of documentation here. So they said that they just need some resistors, but do they have a schematic here? Yeah, okay, install the library, sure. What's the circuit supposed to be? Trigger board. Okay, there's a wiki here, let's see. Mouse of operation, schematic, sure, let's see. What's that? CC. Some op amps here. Oh, come on, black on black. Can we switch to a light background here? Why didn't this do anything? Increase contrast, what? No, I just want light mode, come on. Do I have to switch this in the browser? Oh, come on now. Okay, never mind. Oh, there we go. That's better. Oh, you can't see anything. Oh, come on. Yeah, sorry about that. There you go. So this is the library here. USB power delivery. Right, it supports a bunch of Arduino boards. This is the repo here, and I went to examples, trigger board, right? And this is supposed to be the schematic for the trigger board. All the I don't see. So okay, I think the TX those are supposed to be microcontroller pins here. Okay, so there's some kind of resistor network here, and okay, so there's a comparator here, looking for the voltage threshold. Oh, that's just for level shifting the signals. Okay, and what is the level supposed to be? Okay, this have an explanation. The comparators are needed to level shift the CC signals from 1.6 to 3.3 volts. Okay, and to combine them to a single signal. Why do we need to combine them? Oh, because we got two CC inputs. Oh yeah, sure. So this that like a NOR combination, perhaps. So they invert, and then there are like ORed here. For interaction in sync mode, depending on missing. I see, so it's either for a source or a sync configuration. Okay, and some of the boards don't need them at all, so I guess that depends on probably if the inputs can read 1.6 volt inputs. Okay. And let's see, there's a bunch of schematics here. There's an STM board. I have some STM boards too, but I don't know if they are they compatible. They might not be actually. It's some kind of STM32 demo thingy. Sorry. Might be a DF1 actually. Protoboard for sync. Okay, so anyway, they all use the comparator. I guess we can just use that. Should be fine. So are the CC signals supposed to be 1.6 volts? Sorry. That is interesting. So, okay, I see. So I guess they will, if this is enabled, they would pull down with the 100 ohm and or pull up. I don't know. It's supposed to be enabled high. I mean, enabled high or enabled low. it wouldn't make sense if that was low, and then you would have your 3.3 here, so it end up like a third of 3.3, so like 1.1. Oh, that's a little low. Interesting. Maybe being like even lower with this pull down here. Yeah, so this comparator side here is pretty clear, right? So you get you have your threshold at 0.84, and then just feed the input to the comparators, and that gives them for comparing to your threshold level. Right, now this one I'm not sure about. I mean, okay, they do explain what's happening here. Okay, yeah, 5.1k resistors are pull downs to indicate that there's a power thing. So this is for, but actually for all USB-C, devices that yeah, I think for all devices actually, at least for like the 2.0 compatibility, that's true. So you put a 5.1 pull down to basically signal to the host that your device and you want power. Actually, I have this board I've been designing recently with Łukasz for. I think we are doing. I might talk about it at some point a bit later. Yeah, so you have a USB-C connector here, and yeah, those two 5.1s to ground on the CCs, right? So yeah, so that's typical. But then you have those extra resistors here, and those are connected to the output ports, output pins. Right, and I suppose those are there to bring the output to the right voltage. Now wait those values though, right? If you wanted if we wanted 1.6, like that's gonna be a little low. Alright, so if you let's see, let's get the calc out, right? So you're gonna have your 3.3, right? And then you have the resistor divider here, so it's gonna be 1 over 1/3 basically, right? So alright, so that's gonna give you 1.1 volt. No, maybe. I mean, if your threshold is 0.84, then I guess that's correct. Let's see actually if we can find any specs for this protocol. Okay, there's a note from TI. That sounds good actually. Okay, so those are the resistors. CC logic. Okay, yeah. They have their chips for this too. Okay, so this will probably be for like the dual role. Yeah, exactly. Dual role. Something. Yeah. Oh, so those are the voltages I talked about. So you can go to like 100 watts and plus, right? But yeah, you definitely can get 15 volts. Oh, those are even like required. Okay, that's nice. So we know that if we have a USB PD compatible power supply, that will give us 15 volts. Yeah, and even up to 20. Okay, cool. And with 15, yeah, we can go to 45 watts. Alright, so what's it gonna be in amps? Alright, so if we have 15 volts. Okay, so 45 by 15. So that's gonna be 3 amps. Which is pretty good. Pretty good. Oh, 3 amps at 15 volts. Okay, yeah, so if we were smart and use something like a buck converter to drop the voltage down to our 12 volt supply, we could actually probably even get some more milliamps from that. Okay, cool, but still I don't know how to talk over the CC lines. This I don't care about. So all the special alternate modes on your USB wire. Sure, whatever. Basics of USB Type-C power delivery. Yeah, the same graph. The plug. Okay, but actually this might be how I just fried my USB port on my MacBook, by the way. I've been like probing around on the port. Okay, I have this little breakout from Adafruit for bringing out all the USB pins from the connector. And yeah, I've been probing for something with a scope. Yeah, and now my USB ports are kind of broken on my MacBook, so welp. Okay, still can't find anything about CC lines. I mean, I guess we can just follow the schematic and do whatever they tell us to do there. That's an active cable. It's like another odd thing. Okay, like this is a passive device side. Well, so anyway, that USB thingy is one part of what we wanna try doing, and the other is just building the boost converter itself. So I want this this power supply to work even if we don't have power delivery. So then we just need to run like a regular boost converter. So if we don't have PD, we'll just have 5 volts on the V bus. VRD, what's that? Oh, voltage here, I guess. Okay, sure, but that's still not telling me anything about what communication goes on the CC lines. Okay, I guess we'll just follow that person's schematic and hope that we won't fry our port anymore. Or our power brick, I suppose. Okay, so I have a little Arduino micro here we can use as a starting point. Let me get the OBS thingy. Larger here, right? So I have this little Arduino here, and we're just gonna grab some transistors and inductors, and okay, so we're gonna need an inductor here. This transistor for switching, which will be driven by the microcontroller. We could use a BJT or an FET. Maybe I'll grab a DEC-21700, like, just because I have a bunch of them, and see if we can get that to work. And then we have the diode, so just we can get the current flowing only in this way and charging the capacitor. And then this little voltage divider here is there to bring the voltage down so that we can have the feedback back to microcontroller, so that we know what kind of voltage we are outputting. And then this thing below is pretty much the high side mirrored, plus there is an AC coupling and like a diode clamp. This diode should be on the side of the capacitor, I think. Actually, we'll figure it out. But yeah, basically the idea is we do the same thing we do on the plus side. So we have our inductor, bouncing and making a large voltage here, right, and charging the capacitor. But since we AC coupled here, we are, well, basically not bound to the DC level that is on this side of the capacitor, right? And then if we add the diode clamp here, we basically say we want like if there is a voltage here that needs to be below or below 0 volts, right? Because if we go over 0 volts, plus whatever the threshold voltage for this diode is, if we can use a Schottky diode to make this lower, right? Then it will start conducting, and right, we won't be able to go over 0 volts, right? So the idea is, since we clamp it to the to 0 at the top, it should oscillate. Should start oscillating in such a way that it will, like the bottom, right, of the oscillation, or the like the minimum voltage will be well, way below 0, right, and the top will be at 0. Right, and then we also have this feedback network, so that we can stop switching if we don't need to. Right, actually I have a model here. Here. So here's a little LTSpice model I made, which is well, I don't have a microcontroller here. Just this thing is just here to turn off the switching when we reach the set level. So if I run this, this peaks out around 14 volts here. And stays pretty much stable. So there is a little bit of ripple, but just 16 millivolts. Of course, this is using some huge power transistor with very low RDS(on), and we probably won't get such a nice efficiency from our thing. Yeah, probably not even close. But and just in theory, that works. Okay, so let's see the stuff I don't need. Not sure if this will actually work well on the breadboard. Yeah, I think it should. If we can, like, if this works in like kilohertz range, 100 kilohertz range rather, should probably be fine on the breadboard. I don't need any of this crap. This is also for another project. Yeah. any of that stuff either, actually. No, it's like single-ended to differential converter thingy. So yeah, I did a bit of experiments for the expander protocol for the Kara substars. And yeah, that ended up working pretty nicely actually, but we didn't end up using it yet. So yeah, maybe once we get the Kara substars to the market, we can give you nice expanders with a very nice differential communication protocol. Okay, yeah, we have our board almost clear. I won't be touching this thing here. That's an super top secret filter thing. Yeah. Okay, here we go. So I'm gonna plug the Arduino in. Go in there. Yeah, and we can pretty much start programming. Let me see. It's what kind of annoying USB connector did that one use? Is that micro? Okay, so we've got our Arduino here. Let's grab the ID. Can you sketch? And let's find the board. So it's a micro. Is that the port? Let's see. Good board info. Yep. Maybe I'm gonna run a Blinky just to see if it still works. Okay, yeah, we got a Blinky. Can you see it? And there's our Blinky. Okay, yeah, so then we'll definitely be bringing out the scope for this one later on. But first, need to find an inductor and a transistor. Now, what kind of inductor do we have? I have a bunch here actually. This one might be alright. So it's 3.9 microhenry, and with 1.7 amps. So it's axial kind of thingy. It's actually pretty nice for breadboarding. we'll be using two of those, but for now maybe we'll start with the top side, which should be a little bit easier, since we won't have to deal with the clamping and the AC coupling. Okay, so we're gonna need to bring out the V-Bus. Okay, actually let me grab an Arduino drawing just to make it easier for us. Pin out. Yeah, it's labeled on the board, but I know. Why not have this on the screen too? Now we'll probably use the PWM directly. Okay, where's the V-Bus? Oh, the labeling is awkward, so I'll label it on the right or bottom, in this case, side of the pin. Yeah, anyway, V in is deferred from the bottom on the left here. Let's make the camera large this time. And maybe I'll shift this a little bit. I don't know. Does this work? Kind of. So the first one is going to be V in. Let's break this out a little bit. Oh, actually, maybe I just put this on the rail here. 1, 2, 3. And let's break the ground out as well, since we're at it. So the ground is gonna be the next pin after that. Let's verify we have 5 volts here. Nope. Okay, I'm 1 pin off. Sorry, a bit hard to do this on the camera. Since, you know, the weird positioning I have here. No worries though, we'll get it right. So this is supposed to be our V-Bus, and ground should be here. Let's check now. I grab it in here? No. Still nothing. Let's see. So I'm expecting ground on the fourth. 1, 2, 3, 4, and V in here. And yet not. Oh wait, maybe V in is for the external input. Okay, yeah. Okay, I guess I want 5 volts, not V in. We should. Let's have a schematic for the power supply too. But, and in the micro power supply. Let's see an image. Okay, something like this perhaps. No. Is that it? Yeah, anyway, 5 volts pin should be the one I'm looking for. So let's see again. Ground on the 4th pin. 4 and this should be +5, right? So ground, reset, and +5. No, still nothing here. 1, 2, 3, 4. Oh, come on now, where's my 5 volts? Let's see what this says. Oh, okay, I think I can get. Yeah, oh, wait, what? Okay, yeah, I'm reading the image upside down, of course. Pretend you didn't see that, please. And we're gonna fix our orientation real quick. And now we can expect the ground and our voltages to be here. Let's see that. At least the ground is clearly marked here. And yes, indeed, I'm reading 5 volts. Very well. Very well then. We can now proceed to break those out. So there is the ground. And 5 volts are is going to go on the second rail. Come on, go get in there. There we go. Great. Now I need a transistor. Wait a minute, please. That was my bag of transistors, I think. Okay, so we've got some SOT ones, which we are not gonna be using right now. There is an NPN, 2N3904, we could try that one. And there is old school 2N7000 NFET. What's that? Oh, that's 3906, so that would be complementary to this one, to the NPN. Okay, and that's also a SOT. I think I'm gonna give the 2N7000 a try for this. It's not the greatest NFET. It has a bit of a high on resistance. And of course I'm gonna need to look the pin out up. I don't really remember those kind of things. So basically we want the inductor going from the positive rail to the collector or drain of the transistor, right? And that's gonna be switched to ground. Okay, could use the shutdown. I'm afraid I only have like your regular signal diodes, so that's not gonna be as efficient as we could make it. But I'm afraid all my shortkeys are SMD, so yeah, perhaps I even had some broken out on the board, but yeah. Oh wait, there should be diodes in here from what they just took out from the breadboard. Yeah, there is one. Okay, so and where did I put my inductor baggie? Up there. So let's grab one, and yeah, that's gonna go from the positive to somewhere in here. And we should have 5 volts under now. That's right. Oh, I like this one better. Okay, so there is our FET. Okay, so source gate drain. So drain is gonna be on the right for looking up at the iron flat side. So I'm gonna put this towards the inductor. Also, I don't know, maybe I want to power this from an external power supply actually. It's kind of, I don't know, I don't want to fry my another of my USB ports, and that can make quite a lot of voltage. So let's see what we can do about that. Yeah, I guess instead of taking the 5 volts from here, I could just use the power supply and just connect the grounds together. And then we should be alright. So take this to 5 volts. Perfect. So the source of the FET is, please be quiet. The source of the FET is gonna go to ground. Okay. Now the gate I want to control with an input, with an output of the Arduino. Preferably one that can do PWM. Let's take one of the, oh wait, okay, there are PWMs here and one here. Okay. Yeah, we can make that work. So that's the free. This one. Okay. do I still get 5 volts? I do. This is floating right now. Let's start making some PWM then. Was a PWM example in here, wasn't there? What's that? Analog right, mega. What? So I just want to use the PWM as an oscillator. I don't necessarily care about the duty cycle that much for now. Can I set that? Yeah, okay. Do I need to talk to the registers directly? Okay, no, actually, I don't really care about that. Let's just switch that count for now. Since we don't need a huge frequency, I'm just gonna do this. Turn right. And which pin was that? D3, okay. Delay 1 millisecond, and so we're gonna go with 1 kilohertz or thereabouts for now, and let's see if that does anything. Also, I still need to put in my diode and my capacitor just so that we can have a stable voltage to read. Let's do that here. Like that. And now what kind of capacitor are we gonna use it? So these blue ones here, those are fairly small capacitors, but they have they can take 1 kilovolt. I think that's 18 picofarads or something like that. Maybe let's start with that, and if we are gonna, if we see a lot of ripple, we'll look for a larger one. Yeah, I'm gonna bring out the scope for this. It would be nice to see the waveforms on the output. Oh, and you didn't see that code. Okay. Yeah. Sorry. Kind of suck at streaming at this time. We'll get better, don't worry. I have my good probe somewhere. Probably not. Okay, anyway. You wanna grab the ground here and look at the waveform here. Now this should be at 5 volts presently, and it is, which is good. So let's upload our little oscillator. And now we are down. Okay, let's see what's happening at the gate. Okay, so the gate is high constantly. That's not what was supposed to happen. Wait, is that not the right pin? So there is something happening here. Oh, I didn't say I want to enable the output, of course. What was that? Like pin mode, okay. Pin mode, output. That's what's we are missing, I believe. What's happening here? Oh, did I see a pulse? Sorry, my probe is all... Oh. Well, what the heck? Okay. I'm afraid my phone camera is gonna die in a few seconds. Okay, so that's what? Still under 5 volts. Okay. A string on the rising edge for this one. And there we go. And our switching should be switching control signals here. Huh, interesting. Oh, why am I delaying for 0? And then actually that's kind of what I want though, isn't it? Let's try one. So let's see if I can find the other clip. Yeah. So now let's measure peak to peak on that one on the yellow channel. Yeah. Okay, so we are 6.3 peak to peak. Okay, so we are boosting a little bit from 5 volts. So basically we just need to tweak the parameters, which should be good. Was there a delay, a microsecond delay? Yeah, delay microseconds. Let's try to halve that. Actually, we'll be back at where we were before, probably. 7 volts. Getting there. Probably if we use the larger cap, we could get even better results, but maybe not. Actually, that won't affect the peaks. Will it? Let me zoom in a little bit. Okay, maybe not. Okay, let's double the frequency then. So that's still giving us 7 volts or so. Let's see what happens if we increase it a little bit more. Perhaps we can decrease the low side. Okay, that is a little bit too fast, I think. What if we made the other parts shorter? Okay. So the bottom of the wave went down, and Yeah, we are already 12 volts peak to peak, but actually what we are interested in is not peak to peak per se, but rather the maximum voltage we are reading, which is already 20 volts. Ladies and gentlemen, we have 20 volts output. Now, there's a lot of ripple here, obviously, but we can put in more capacitance and smooth that out. Actually, I have more of those blue ones, maybe. If I just put a second one here, how would that change a lot? Let's see. Not much. I don't remember what's the voltage rating for those 100 nanofarads I have here. Let's try that anyway. Maybe it won't explode. Oh wait, I didn't plug that to the right hole. Did I? Yeah. See? Okay, that did help a little bit. Let's try the 100 nanofarad one. Oh, there's no capacitor. Now I'm plugging in 100 nanofarads. And ladies and gentlemen, we get a stable voltage, just like that, 15 volts. Actually, exactly what I was going for. Let's zoom in a little bit. Oh, not much happening here. I'm gonna AC couple the first channel, our output, and zoom in, and let's see if we can see any ripple here. Wow, this is super flat, but we don't have any load yet, so let's try some resistors now. This I believe is 100k. Let's see, check. My resistor here. No, this is 50 ohms actually. What's that? Is that the 10k? 1k. Okay, actually, let's try 1k. 5% battery. And oh crap, we are current limited here actually. Let's give it a little bit more current. Oh man. And what kind of voltage are we making now? We're making 70 volts. Okay. Okay. It's perhaps a little bit more that I wanted, but that's good actually, because now we can try and make a feedback loop for us. But first I'm gonna plug my phone to charger so that we can keep going. And also I'm gonna use the lamp power supply as the phone charger, because what's the worst that can happen? There. Please charge. Okay, yeah. Yeah, it's good. Maybe I take the gain down a little bit more, and I don't know, either I'm gonna be very silent or you're gonna get a lot of noises from the room. I mean, that's the best I can do for now with this mic setup. But perhaps this isn't so bad. Okay. At least I can kind of hear myself talking, so that's okay. Now we wanted to make a voltage divider. Let's see. I think I had this computer already. Okay, so something like 14K to 1 should give us a 1 volt, a nice 1 volt output from 15 volts. So let's see if I have any resistors I can use. If not, we're just gonna put some in series. My resistor box is here. Okay, what do we have here? So those are hundreds and 10 and 1K, so those can go to the side for now. And let's see if we have anything that can make 15K. Or 140 actually would be nice too. Unfortunately, the shape of this resistor box is getting a little bit messy. Okay, so 270, do I have any of those? No. Fortunately, no. Those would be nice. 80. That's a little too high. Oh, okay. I have 6.8. So if I put two of those in series, um, should be pretty close to 14. So here's one. Here's one. And here is 2. And now I need a 1K to finish the voltage divider, which I have in the buggy. And that's gonna need to go to ground. Okay, maybe I'll put that here on this side actually. Kind of starting to get a little bit annoying here. I don't really like breadboards, to be honest, but yeah, kind of works for what we need here, so yeah, let's go with that. Okay, let's see what we can read here. And nothing. Okay, that's too low. Why? So here we had like 70 volts, right? I'm gonna try not to touch this because that's quite a bit of voltage. Wait, it's 8 now? Oh, maybe my... Yeah, I guess my resistor network pulled it down. Okay, so it did not enjoy the load. What if I give it a bit more current though? Ah, yeah, there we go. A little bit of amps and we are good again. Though, yeah, that's very inefficient. But oh well. Oh well. Maybe we can get the frequency a bit higher though. Because we are still kind of low here, so let's see. Okay, we are out of range here again. Oh, 24 volts. Not bad. Not bad. Okay, now I want to read the feedback voltage. Okay, yeah, it's lower. So, yeah, I think that checks out more or less. So we get 2 volts and average for, what was it, 20 volts. And we wanted 1 volt for 15, which is a little bit low, but also there is noise on here, so okay, I guess we can put in a smoothing capacitor. That just not too high of a value so that we can track the changes quickly enough. Okay, again, this is getting a little bit annoying in here. Just a little bit. Getting there. Come on. It's gonna be another mumbly stream, isn't it? Okay, let's... Oh, God. Let's see now. Not much more stable, to be honest. Yeah, it didn't do anything. And also, why are we overcurrenting? And that's something I'm going to do with my scope probe here. Am I shouting something out? Perhaps. Let's try with the 100 nanofarads again. And again, turning it off, just not to shock myself. With the volts we are making. Yeah, I know. There. And maybe let's put the probe on a little longer wire here. Also, I really need some new probes. Yeah, that didn't do a lot. I want to see the frequency on channel 2 though. It should be more accurate because it's a square wave or a rectangle. Okay, so we are 20 kilohertz right now, so still not that high. And also we are taking 200 milliamps just to power this little resistor network. So, not so great. Not so great. Let's make it go even faster then. Let's see, how about 2 and 5 microseconds? Can you do that? Oh, okay. You can, and again we get some kind of high voltage there. I wonder why the filter capacitor is doing such a poor job though. So a lot of crap on this. Maybe it's just getting interference. I don't know. I don't know, man. Let's take a look in here. Oh yeah, that's just interference on the probe. Okay. Okay. Yeah, that doesn't do any. That doesn't make any difference. How is the power doing here? Yeah, also very spiky. We should perhaps add some more filtering here then. Yeah, I don't like those spikes at all. Let's see what kind of cap we can get. How about one of those big ones? Okay, so the left rails are ground here. Oh, did it work actually? Huh, see, it's clean now. Oh, almost. Yeah. Yeah, that's a bit better. Let's see what's the peak to peak. 2 volts. Well, that's a bit much. Still. It's probably just the large, the short peaks. But if we add a 100 nano in parallel here. much of a difference. Anyway, we are making volts, so that's nice. How many volts are we making? A lot, apparently. At 30 volts, okay. Yeah, 30 volts with the, what was it, 15 or so kilo ohms of load, which is, I guess, fine for a POC thingy. Now the next thing I want to do is read that feedback we made here, which again we wanted to see how stable it is. Yeah, it's better now. It is better. So 2 volts actually, almost, for, what was it, 30 volts, right? So we wanted 1 volt for 15, so yeah, we're closer. Let's see if we can do a read here. Well, analog read on that pin here, which was what? No, not this one. We need to bring it in first. So voltage from here. So we are over current again to some kind of analog input. This one here should be fine, I guess. A5, D23. Which I guess is here. So I want to set a reference here. Can I do that? Analog reference. And yeah, what kind of references do we get? AVR boards, so that is an AVR board. Oh, but it's a Mega, so one of those, I guess. Does it not have a 1 volt thing? Okay, 2.5. 2.5 would be fine. Let's Okay, let's use 2.5. Can we do a comparator with this board? Or does it have a comparator? I guess would be the question. There is a library. Okay. Okay, I guess I'll just do an analog read. Okay, so what pin did we use? This thing here, right? So A5. Analog read resolution. Okay, I guess it's not on the micro. So we just get 10 bits, which is fine. Now to get let's see, to get 1 volt out of 2.5, that's gonna be 0.4, and that's 10 bits, so 2 to the 10th, so 409 should be the reading. Right. So first of all, we're gonna print this, and now actually let's start with that. If is less than, so we're just gonna do a simple on-off regulation. That might be enough, although we probably will need to smooth the feedback value because we're still getting some noise there. Well, let's see how that works. Okay, there is an internal 2.5. Okay, so is the documentation lying to me then? Reference. Where was it? Oh yeah, it's a micro, not a nano, but still. Arduino micro, let's see. 2.56. Is that the same as the Leonardo thing? Ah. Okay, how about this? Also no. Internal. Let's see. Which mega do we have? I don't know. Okay, Okay, I guess let's try internal and see what this gives us. We are not going for like absolute precision right now. Just a proof of concept. Volts. What kind of volts do we have though? Tell me the volts. Nothing? Well, how is it nothing? Are you kidding me? First of all, what happened to the trigger? Was supposed. Okay, I guess. I didn't set it. But still. Okay, I think I just going too slow now. Because the analog read is taking a bit of time. Is there like an asynchronous read or something in the Arduino library? Start read. So I want this to read asynchronously, so that I can keep my oscillator going. If I can't do that, I suppose I can just run this oscillator in a timer interrupt. Yeah, that's a better way anyway, probably, so let's do that. Timer interrupt. Oh, that's a library, okay. Wait, is that not built in? No way, that's not built in. Really? Okay then. No way, there isn't a built-in timer. Why the hell did I go with an Arduino for this? So what's the range? 8-bit? Analog, right. No resolution, okay. Eight bits is default, okay. And also the only thing for AVR boards, sure. Okay, okay, so let's do 127. Otherwise we disable the PWM, so that's gonna be 0. So right now I don't care about the duty cycle, I just want to have an oscillator output here, and that gives us 1 kilohertz, which is kind of slow. Okay, are we making any voltage? No. No, we don't. Huh. Okay, that kind of sucks. I suppose that's because we... Oh, okay, we're not making any voltage because the power supply is off. Oh man, oh man. Okay, that's better, but we are still way too slow. Frequency. Let me set the frequency, god damn it. Or is that the best we can do? Okay. Sorry, but this kind of sucks. I could have just used a better board, I guess. Like, how is there no timer interrupt? I can't believe it. Useless. Okay, let's see what the analog read does. Mm-hmm. Okay, so we just do this, just this while loop. And really, you couldn't give me an async version of that? What? Is it 32? Oh, what kind of micro is done that? 32 U4, yeah, that's it. Okay, what the hell is that code? Okay, sure. Okay, we don't even need that. We're pin free. Whatever. I don't know. Do we have that? I guess so. Whatever. Actually, let's copy the whole thing. Max, yeah, sure. Yeah, if we don't have ADC. Okay, sure. Why not start with that? Sure, so we're gonna start the ADC conversion. Actually, let's do that in the setup. Free. No, we can define the pin as free. And also, what? No. pin is A5. Right, and then we're just gonna wait for the conversion to finish, but not gonna block. So only if the analog read is finished, we can actually read out the value of the feedback. Otherwise we can keep going. Also, let's not do the PWM. I just want my good old digital write. What? Or is that defined? Wiring private? Okay, that's just a bit number though, so I can just set it like this. One, probably. Yeah. What? Analog reference. Where do we set that? Okay. So I guess that's gonna be internal. There we go. Okay, looking good. So we got a higher frequency and we get some volts. What kind of volts do we have? 30 something. Okay. Okay. We aren't reading any value though. Okay, did that not work? Why didn't it work? Should we just use that? Okay, I suppose something could be clearing it in the meantime. Ninety-six hex. What does that mean? Oh, it will read as one when the conversion is in progress. Okay, so we want this to be 0 actually when it's done. I see. Look at that. We are stopping the can they boost? It's not a very pretty waveform we're getting though. Let's zoom in a little bit. not sure what's happening here. Is this is the ADC just too slow? It could be. I mean, I suppose we could make a comparator and plug that into digital input, but I really wanted just to use the single chip, so that would be kind of pointless. Also, what kind of values are we reading here? So yeah, so this is what the ADC sees, and this is what's actually happening. Now, I'm not sure what the sample rate is. Actually, why don't we skip the serial printing? That could be slowing us down. Okay, that's different. Let's check something else. Add mega 304. Oh wait, 3204. Sorry. ADC noise canceller. And that's the wrong chip. I wanted at mega 32. Comparator? Yeah. Oh yeah, we already looked at this one. I really don't want to dig into the specifics of the ATMAG right now. I guess we could make this a bit slower again, just so that the ADC can keep up. Let's see what happens if we have the frequency, switching frequency. Not much. Okay. Let's make it much slower. That's kind of more stable. How about the output voltage though? Okay. Yeah. 13 volts. Okay. There's more ripple though, but that's okay. Ish. And now it's running all the time though, so it might be too slow. Wrong wire. Mm-hmm. Yeah, I guess we really need a comparator, don't we? Should we chat GPT this? Hmm. Hmm. Should we give this a try? D6 and D12 would be our input pins. Let's see, does that make sense? D6, yeah, it's an ADC pin, and D12 is also an ADC pin. Okay. There's the comparator, so it's D7 and D4 actually. So yeah, are you lying to me, ChatGPT? Also, when does it specify an analog comparator if there is no library function for it? I think we did actually plug into... No, we didn't use A6. We used A5. Oh. Anyway, let's try that code. Actually, I do want to use the band gap reference as one of the inputs. What the heck? At mega. So I want to put the output of the comparator on one of the pins. let's use this one here, D16. 16. And the output, I suppose, is the ACO. No, I do want to use one of the I want to use the bandgap reference into one of the inputs. What's the value of the reference though? Internal voltage reference. Yeah, but what's the voltage? 1.1. Oh, perfect. That's exactly what I want. Well, almost good enough. So actually I want to enable that. So I guess A in 0 would be our input then, which was here, D7. Okay. Okay, let's load that in and see what happens. Now I also don't want this part any longer. Oh, so I put this inside the setup. Yikes. So this is high. That's constantly high. Okay. Ah, yeah, because we haven't plugged in the input yet. So that was supposed to go to the 7. Here. Yeah, and we are monitoring this pin here. Let's see. No, still high. Okay, are we comparing or are we not comparing? So why are you lying to me about the pins? Oh, maybe this is lying to me actually. Huh. Yeah, actually, let's take a look at the voltage and the feedback line. That perhaps will be more informative. Since that's what we are comparing. Yeah, but it's low indeed. And if we go higher, no, nothing. Oh, wait, no, that's 7. Okay, so they are using D7, that's alright. Okay, so this is the comparator bit. Is this the same that what we're doing? Is this the same thing we're doing? Let's see. So we're doing a little bit more, I guess. Multiplexer. Okay, disable the multiplexer. Why? Okay, had a nice drawing with the ATmega 32U4 spec datasheet. Okay, yeah. This thing here. Okay, so that's the multiplexer. Aha. Acme ADN. Okay, so we need to choose the input, I guess. Aha. Okay, so we can... Wait, why do they disable it? ADCSRB. Okay, so that is correct. We should... Really? 0? Okay, so we could have used the analog input pin as an input to the converter. Or I guess you can disable the multiplexer. Why is this so weird? Okay, but we don't enable ACME, I suppose. In the end, this thing is always... Oh wait, we didn't set an output here at all for the... What's my setup? So I want pin 16 to be an output and initialize it with 0. Okay, and it is low. That's okay. Now if we make this, yeah, it should be triggering at above 1 point something. All right. let's just write AC output in the loop. Why not? So it's high. And then it's also high. Great. Okay, I'm supposed to. So that's a bit. Okay. That's a bit. Oh, of course. And now it's low. And then it's also low. Ah, god damn. Useless. Okay, wait, so if. Okay, maybe it's the other way around. So if the multiplexer is disabled, then it's gonna use the bandgap reference here. Okay. AD enable. Not AD enable. What? Wouldn't you mean an A in minus and in negative can only be connected to the multiplexer? Like you're telling me that it can be connected to bandgap reference right here. So which one is it? Also, why those two? What's ADN? So this is the multiplexer enable, okay. And what's ADN? ADN, let's see. ADC something. Ah. Okay. Okay, so we are going into here. And ACBG must be off. Wait, so actually this is the other way, or it should be the other way around. So this is for A in 0. Then we want to disable the bandgap reference. And the negative is supposed to go to the bandgap reference. Ah, this is so weird, bro. Okay, now let's try it again. Yes, yes, thank you. God damn it. There it is. There it is. So it's triggering at like 1.2, which is, I suppose, where it was supposed to be. That's good. That's good. And it's low if we are below. That means, yeah, if this is high, then we run our oscillator, our little oscillator here. Good, good. Yeah. Very nice. Okay. Or did I get, yeah, maybe I got it. Did I get it the wrong way? Oh, yes, I did. Yes, I did. Okay. Okay, let's see that voltage. First. Yeah, we are a bit too high, but I guess we should just tweak our resistors now. And we can get it to where we want to be, right? So if it's if the reference is 1.2, let's see. So let's take a look at our voltage divider here. So I assumed we have 1 volt. Um, all right. Oh, that was for this one here. You know what? I'm kind of tired. Really, it's 4 a.m. So I think we're gonna wrap it up in a moment. So, of course, it's not a very efficient converter right now. We're burning to 30 milliamps to do what, like, oh, I think we already calculated it, didn't we? So right now we've got an 80 volt output, and the resistance was what, like 15k. Actually 15k. So to make 1.2 milliamps, that's awfully inefficient. But I mean, we can tweak we can use a better inductor, we can use a different transistor, so there's definitely a space for improvement here. Again, for now, I just wanted to see if we can make it work at all. And also, like, the voltage is higher than we wanted, but that's just the voltage divider here. Actually, can we do can we solve equations with this? That way I wouldn't have to think. Okay, so let's say we've got our 1k and 1k plus some resistor value, and we want okay, so that's gonna be times 15 volts, right? And we want this to be equal to 1.2 volts. Okay, so we want around 11 to 12k. 12k, do we have that? Do I have a 12k here? Let's see. Yeah, screw the box. I'm just gonna use a 10 in 2 ends. Thousands, of course. That's a 10. And those here. I'll get some ones in here. That should do. Let's see. Nothing. What did I do? Okay. Yeah. So that's 17 max. Okay. Give me the average now. Okay, yeah, we are at 14.8 average, so not bad. Not bad. I guess I can put a large capacitor at the output to smooth it out a bit. And although the ones I have here are a bit low voltage. Let's see, I think I had a better one in the box. My box of cups. This one. Oh, it's a third. Okay, I guess those are those Panasonics. Don't know, but they are 50 volts at least. 1,000 microfarads. Oh yeah. I'm gonna put in a millifarad. This one has nicely bent leads. Has nicely bent leads. Let's try that. Although, okay. we can. Let's see if it explodes or not. Very smooth indeed. Okay, it's rising, and there it stops. Okay, not bad, very smooth. Very smooth indeed. Okay, so we managed to get our analog comparator going. Okay, great. Great. Yeah, great. It's exactly where we wanted it to be. If we increase the frequency again, what did I use before? 5 maybe? I don't know. Let's see. Look, we have a better efficiency already. And yeah, now it's stopping a lot more frequently. Very nice. Should we go faster? Let's see if we can go faster than that with this chip. And ooh, yeah, even better now. Very nice, very nice. Okay, so not only we are pretty much spot on 15 volts, the efficiency is already better. I mean, I'm not sure that yeah, I'm not sure how accurate those current numbers are, since it's, you know, pulsed current, I suppose. I could use the meter to get more accurate reading, probably. Anyway, pretty good. But we are smoothing the input a little bit, so maybe it's kind of accurate. Also, like Unity, please make this wave display like scalable. It always gives me current, like in this huge. Oh, you can see, right? There you go. So there is a trend display in this power supply, but it's scaled. The scale goes to like 6 amps, I think, and you can't zoom in at all. So yeah, why? You can read the stats probably with like via USB or LAN, but why not make it zoomable? Should we try going even faster? Let's see, 1 microsecond. It should be 1 kilohertz, right? 100 kilohertz. Okay. Sorry, 100 kilohertz. Right? It's no, megahertz. Really? Yeah, but they're not going that fast. Anyway, yeah, it's kind of good enough though. Okay, yeah, I guess that was a very fun stream. We did fight a little bit with the AVR. We did manage to get the comparator running. So now we are comparing our feedback voltage to the built-in voltage reference. So like 1.2 volts apparently. Yeah, and if we are short at voltage, we run our oscillator that switches the where's that drawing? So basically what we are doing is switching this transistor here, which causes a voltage spike on our inductor here, and that lets us get a higher voltage at the capacitor, which then smooths it out, and that's how we get our 15 volts output. Now, that still is not very efficient, and probably with a higher load it would struggle, since again we are right now taking like what was it, like, something in the order of a milliamp just via our feedback network here. So yeah, and you can see that it's not running all the time, but still it's running quite a lot of the time. So yeah, so we can guess that if we increase the load, it will have to work more, right? So again, we can try optimizing the components next and try to improve that. And then we can probably get significantly better results, would be my guess. I'll probably try switching out the transistor first, and also make a real board for this instead of, instead of the breadboard here, since the connections are probably have some resistance and or impedance. And I have some SMD inductors lying around, so I might actually make a board for this. So what's left to do here to get the full POC of what I wanted this to do would be to now add the negative side, which we can do in a similar fashion. We just need to AC couple the output or like the part after the inductor here. Clamp it with a diode, and then the rest would, and then we can add another smoothing capacitor at the output. Right. And that should give us our 12 volts, and also it would have a similar, feedback routine going on for the opposite side. Although we have only one comparator, so I guess we would have to use the multiplexer, the ADC multiplexer to check both feedback voltages. Which is something we can do probably. But also, yeah, I would probably be using a little bit more capable MCU for that, since what we have here is kind of struggling. I have a couple of those AVR16DD series chips, which are kind of okayish, so I could try doing something with those. Probably. They are still very cheap and a bit faster than those old AVRs, I think. Actually, I don't know what frequency this runs on, but those can go to 48 megahertz if I recall correctly. Do we have anything about? Oh yeah, so this micro runs Arduino micro runs at 16 megahertz, and those AVR-DD series had a little bit more sensible peripherals, I'd say. Perhaps a little bit more modern. Okay. So yeah, I guess we're done for today. I'm kind of too tired to keep going with that, but yeah, we are like third of the way there, so we would need to do the other side of the other rail, the -12. If we wanted to do 5 volts, I guess we can just drop down from the 12 volt rail with a linear regulator or something, or back converter maybe. We can't really use the 5 volts from USB directly, because that again will be can go up if we use the power delivery, right? And then the power delivery itself is the third thing we would want to do. So yeah, so we need to implement the PD protocol. Probably just using this library here. Yeah. Oh, there's quite a lot here. I think they put a lot of effort into this library. Let's see. Yeah. Yeah, so that's worth looking into. Yeah, we would have to implement this interface to talk via DCC. The thing is, this is also an Arduino library, so we are kind of stuck with Arduino. So that kind of limits our options in terms of what kind of MCU we could use. The small AVR 16DDs are not supported as far as I know. I saw there was someone trying to port Arduino to that, and I'm not sure how complete that is. It's kind of I mean, I don't know. Maybe there is something, but it's probably not as stable as those official Arduino releases or the Adafruit stuff even. So yeah, we could use SAMD. I have a couple of those too, but that kind of feels like an overkill for what I'm trying to do here. But I guess they aren't like super expensive either, so yeah. And I have a large spool of some D21s, so there's that. Yeah. So overall, I think we are onto something here. Yeah, I'm gonna get some sleep, and I have some important business tomorrow. So, cheers and have a good night, everyone. I'm gonna shut this off now. And yeah, there we go. Good night.